Good morning, everyone. Good afternoon, good evening for our friends around the globe. Thank you very much for attending this presentation. My name is Serge Guiteres. I am the Senior Business Development Manager for the Doble Morgan Schaefer Altanova for the online monitoring system, specifically for DGA, for Asia, APAC, the India and Australia region. Today, I'm going to talk about the importance of DGA, the accuracy, how important it is for DGA, and the impact in the diagnostic, when you're using some of the DGA diagnostic tools, and also how to read some of the spec sheet of the different product, to understand each of them, what they mean when they are referring to either the low detection limit or the accuracy of their system. So let me start the presentation here. Okay. Okay, good. So just let's go over a brief review of why do we do DGA. As you know, our transformer are using oil. Mostly 95% of transformer are using mineral oil around the world, mostly for two reasons. One, to use that as a cooling fluid to remove heat from the core. And the second one is an insulation. Now, the major oil that's being used is mostly mineral oil. And mineral oil construction, comes in mostly different form. The majority of them are what we call linear chemical form, like this one, where you have carbon, the atoms that are attached to each other, and hydrogen on the extremities. But also mineral oil has different configuration, either in what we call drench or mostly aromatic. But overall, all those mineral oil behave mostly the same way when they're subject to a thermal fault or an electrical fault. So what happened in your transformers? Well, as your transformer is energized, the electrical and the thermal stress, energy start breaking the connection between the hydrogen atom to the carbon atom. Now that connection, that chemical connection, is usually what we refer to as very, very weak. So it's very easy to break that connection. So in a normal transformer, in a normal operation, there will always be a certain level of hydrogen that is being dissolved into the oil. The level depends. It depends on the age of the oil, depend of the load of the transformers, depend of the mineral oil and the design of that transformer. Our experience, we've seen transformers today that on normal operation generate level of hydrogen of around 2 to 5 ppm, but also we've seen other transformers that generate level of hydrogen up to 500 ppm in a normal operation. So you have the whole range of it that you see. The other gas that are generated in normal operation is carbon dioxide, carbon monoxide, and both gas are coming mostly from the degradation, the continuous degradation of your insulation paper. And those gas always usually continuously increase over time as your insulation paper mostly will continue degrading during the life of the transformers. Now, the other gas that we're looking at in the DGA, the methane, the ethane, the ethylene, and especially the acetylene, now those gas are normally not created in the normal operation of a transformer. Those gas are created when you have, a thermal or an electrical fault that start developing. Now, each of those gas are created at a very specific temperature. Methane start appearing in your oil if you have a fault. The fault temperature is over 140 degrees C. Ethane start appearing at around 250 degrees C. Ethylene is around 350, and acetylene is over 500 degrees C, up to 1200 degrees C. So what happens is when you do a DGA, depending of the gas that you find in your analysis, right away it gives you already one piece of critical information. It tells you specifically what is the minimum temperature of that fault? So if you're starting seeing methane, well, right now you know that mostly your fault temperature is at least 140. And if over time suddenly now ethane start appearing, what it means is that fault is evolving and it's gone from maybe around 140 to 250 plus. So the DGA, that we've been doing now since the mid 60s, is to mostly design to measure those gas and give us that type of information right away. Now, why those gas are created? Well, as the temperature of the fault increase, as I said, from 120 to way over 700 degrees C in acetylene, up to 1200, the temperature of the fault generates a lot of energy. And that energy create those gases. So if you start seeing methane in your DGA, methane carry mostly around 338 kilojoule per mole of energy. If you start seeing acetylene carry mostly 3 times more energy, require 3 times more energy to be created in your. And this is why people are much more worried when they start seeing, especially ethylene and acetylene, because those two gas, carry a lot of energy, plus the hydrogen that's also generated. So if there's a very high level of those gas, and if you have a spark, well, then that's usually what you will see, a catastrophic failure of your transformers. So this is one of the reasons why those, especially acetylene, is a gas that we look at very carefully, and often tells you that you have a major fault, because at over 700 degrees, usually it's an arcing problem. Another way to look at it is this chart. This chart tells you the rate of generation of the gas depending on the temperature. So what this thing shows is that when you get to around a temperature of around 140 degrees, the rate of generation of hydrogen increase. And as a fault will mostly develop, so the temperature will increase from 140 to up, as I said earlier, to potentially 1200 degrees C. Hydrogen rate of generation always increase. So the temperature, as a fault change and an increase in temperature, you're generating more and more hydrogen, and the rate of generation accelerate. For methane at 140, now you're starting seeing a rate of generation of methane, and it will the rate of generation increase up to a certain temperature. If that temperature of the fault exceed 240, 50, now you're starting seeing ethane. So as ethane rate of generation increase, the rate of generation of methane diminish. And it continue like that. So the next thing will be the ethylene. As we'll reach the temperature of ethylene to generate ethylene, the rate of generation of methane and ethane start decreasing, and the rate of generation of ethylene increase. And at 500 degrees, between 500 degrees and 700 degrees, mostly the rate of generation of acetylene is very, very small. So usually, in your DGA, when you start seeing acetylene that start appearing in your DGA, when you're still seeing 1, 2, 5 ppm, usually you're in this area. As soon as the fault temperature increase over 700, that's where you will see the generation of acetylene accelerate. And this is where you get in an area of potentially failures of your transformer, because you have a huge amount of acetylene that's been generated at the same time that a very, very large amount of ethylene is being generated. So, but there's two, mostly when you look at this, there's only two gases that are constantly increasing, hydrogen and the acetylene. And what you have is mostly what you call a domino effect. As the fault evolves and the temperature of the fault evolves, one gas rate of generation increase and decrease when another gas rate of generation increase, until you reach the point where mostly you're generating acetylene. So when you have a DGA, a very accurate DGA, that just by measuring the gases, it gives you a lot of information. Where do you stand into that curve, that graph, to tell you exactly potentially where you are from a temperature point of view. Now, why accuracy is important in DGA? When you look at the IEC 60567 spec, what it says is that mostly the accuracy should be less than 15%. So when you're measuring something, every instrument has an accuracy range, plus minus 5, plus minus 10, and there's, all that depends from a lot of different factors. But to do a very good DGA diagnostic using the DGA diagnostic tool that have been developed over the last 40 years, you have to have your system accuracy less than 15%. Now, accuracy, you have to look at accuracy short-term and long-term of any kind of instrument that you're looking. Mostly short-term because it's mostly when you have your equipment is brand new, so you know what kind of accuracy the system is going to deliver. And long-term because as the system age, the electronics start aging, the detectors start aging, the extraction system is getting old. Also, the accuracy, you start losing accuracy. Now, one way of making sure that your long-term accuracy stays at the same level than your short-term accuracy is mostly to have some kind of calibration system. Either you in the lab, you calibrate manually your system on a regular basis, or on online monitors or portable system, that they have some kind of a regular calibration. So you never lose the accuracy that you had at the beginning when you buy those systems. Now, why the accuracy is important in diagnostic? Here's an example. We took mostly Duval triangle, that is mostly widely used around the world. And you can see here with the X, this is the exact measurement of whatever gas sample we had with zero accuracy. So it's, if there was 100 ppm in that sample, it measured 100 ppm of all the gases. And we put the results into the Duval triangle. So here it tells you that mostly you have, for that particular sample, you have potentially a thermal and a dielectric fault that's happening. As the accuracy start increasing from 0% to, on this example, to 15%, now the results start moving away from that optimum diagnostic point. So you can see here the red dot. So the pentagon you can see here, this what tells you is the surface of uncertainty in the accuracy measurement and the accuracy of the diagnostic. And what you can see here is that now at the 15% accuracy numbers, potentially you're going to have a diagnostic that falls off the real diagnostics. Now you're in what we call the D2, which is mostly just a dielectric fault high energy, or potentially the system can give you a diagnostic of a T3 telling you that you have arcing. So, this is the impact on the diagnostic as the accuracy increases. And that's why the standard says that you don't want to be more than 15% on that accuracy, and even better. So as the accuracy gets better from 15%, let's say, to around 5 to 6%, well, that surface shrinks significantly around the optimum diagnostic point. And what it means now is that the accuracy of that diagnostic increased significantly, and that's mostly what everyone is trying to get during a DGA. Here's another example visually on what will happen if you move from a low accuracy system to a high accuracy system. Here we have a measurement, the optimal measurement of the different gas for methane, ethylene, and acetylene are here. And we use a system that has an accuracy of plus minus 30%. And when we plug them into the Duval triangle, you can see that some of the diagnostic tells you have a D2. Some of them, many of them, the diagnostic tells you that you have a DT, and potentially you're very close to a D1. So potentially with a 30% accuracy system, the same sample can give you 3 different types of diagnostic. Now, if we take the same sample and put it in a system that has a 5% accuracy, now you can see that all the results, all the diagnostic are much more concentrated in one area. mostly in the DT. Some of them are just borderline with the D2, but again, the surface where all the diagnostic fits is much more smaller now, with a better confidence that this is the exact diagnostic for that sample. Here's another example again, a much more higher gas concentration measurement with the same system accuracy of 30%. Here you can see, a lot of the diagnostic falls into a D2, a T2, who's mostly thermofog between 300 and 700. Some of them are very close to arcing, and some of them are in the DT. You take the same sample, you put it in a system accuracy of 5%, and now mostly all of them are concentrated into a T2 diagnostic. So this is the impact, especially when you're using the Duval triangle. That you can see that it really concentrates, the diagnostic in a much more tighter area of the diagnostic. If you go from a very high accuracy to a very low accuracy system. So let's look at a different way of doing DGA. Now, since mostly the mid-1960s, when DGA became standard around the world for transformers, the process, especially for the lab, is a very lengthy process. You go from going to sampling points, taking different type of sampling technique and location. Usually, the majority of people are trying to use the drain valves, using syringe, using containers. Then usually the product is packaged, sent sometimes in a very close area where the sample has been taken, sometimes very, very far, depending on the geography of the country and where the DGA labs are. When it gets to the lab, well, the sample will wait, depending on the lead time of the lab. Then they have to prepare the sample, then you have to extract it, and then you have to do use mostly GC to separate the gas and measurement. So when you look at that process, in an ideal situation, if you had 100 ppm of gas in that transformer, well, you would like to see the results coming out of that GC at 100 ppm. That's the ideal situation, and it never happened. I mean, the whole process, there's too much handling, there's too much time waiting, to have absolutely no error in managing the sample, no chance of losing gases. So what is the reality? Well, in the best case situation in general, if everything is under control, you flush the drain valves before you take the sample, you take a container that is very high quality containers, because there's containers and containers. Some of them look good. They have absolutely no seal, especially for low molecular gas, so you lose them during transport. Some of them are much more better. The transportation time is absolutely critical. If you can transport the sample to the lab in a couple of hours, it makes a big difference if it takes 2-3 days, because you have to fly it to another country or another part of the country. And also how long that sample will sit at the lab. Will the lab process it in a couple hours, or they will process it in 1 week? So all that has a major impact on the final measurement. But the best case situation, if you start with 100 ppm, if you get the results of around 86 ppm, so the whole system accuracy is around 14%. In general, you're still under the IEC spec, and you have a higher probability of doing the right diagnostic using the diagnostic tool. Unfortunately, the worst case scenario we've seen, and we've seen it many, many times, is you start with 100 ppm and you get results of 70 ppm or even worse. And that, you have to be knowledgeable, or you have to recognize that, because that will have a huge impact on the diagnostic, and will have a huge impact on the decision what you're going to do. Just to show you the impact of having a good lab versus not such a good lab. Years ago, quite a few years ago, IEC Seagray did a round-robin test. What they did is they asked labs around the world, around 130 labs, if they would like to be in that study, and mostly all of them said yes. So what they did is that they sent to those labs what we call gas in oil standard. So it's a specific oil in which a specific quantity of gas has been dissolved very, very carefully, very, very tight spec. So what they did is that they sent those samples with no information on them, just an oil sample as it is, to those labs. One of that sample has what we call medium gas concentration, so it's mostly around 100 ppm. And one of the sample had low gas concentration, around 10 ppm. And they asked those labs to measure them and send back the results. And then they compare the result they got from the lab versus the sample that was sent. And what you see here is the results. So the best lab for the medium gas concentration, we're measuring it plus minus 3%. It was incredibly very good. And for the last gas concentration was plus minus 22%. It could be expected considering when you get to 10 ppm, a very small error, just missing 1 ppm is an impact of 10%. The average lab in general for the medium gas concentration were plus minus 15%. And that's mostly in line with the IEC 60567. But when you look at the worst labs, some of those labs came back with the result of plus minus 65%. So what it means is that for that lab, the same sample that was sent to the other lab, their GC, their extraction system and their GC, had an accuracy of plus minus 65%. So if you send 100 ppm, well, they measure only 35 ppm, meaning that result, frankly, you cannot do anything with that result as far as diagnostic. So what this thing shows is it's very important when you have a lab, when you choose a lab, to make sure to understand what is their accuracy, especially in the medium gas concentration, to make sure that they're under that 15%. How do you do that? Well, it's pretty simple in a way. One way of doing it is to use gas in oil standard. In the ASTM 3612 or the IEC 60567, they really specify what kind of gas in oil standard can be used and how to use them in the GC. So by sending that sample that the specific concentration of gas in the oil to a lab and getting the result, you will know very rapidly how good that lab is from an extraction point of view. Is their extraction efficient, depending on the extraction system they're using? And also if their GC is very good at separating and measuring correctly the gas in the oil. So a gas in oil standard tells you not just that the GC is calibrated, but also that the extraction system is efficient. So usually what you do is that you send a gas in oil standard like this one, where you have the specific concentration of the gas that are dissolved in that oil with an accuracy of plus minus 5% in general. And the lab will mostly inject it. And here's an example of a lab where we've worked with, where we send 100 ppm gas in oil standard. What the blue and the square red is the range of that gas, based on the spec plus minus 5%. And the green triangle is the measurement. So on this one here, on this GC, you can see that mostly for all the gases except on the hydrogen, they're measuring exactly, what is the amount of gas in that oil sample, except a little bit here on the hydrogen where they measure slightly a little bit higher. The same GC, we use a much more higher level of gas at 500 ppm. And now you can see that, again, for the hydrogen, they're measuring slightly higher, but for the other guys, they're mostly in spec. And on the acetylene, also, they're slightly a little bit higher. So except those 2 points, in general, that whole system seemed to, that whole lab GC system, extraction and measuring, seemed to be pretty in line and pre-calibrated. And that gives you the confidence that when you're going to send an oil sample, the DGA result you're going to get has a high probability of being pretty accurate. Now, when you look at other way of doing DGA, now the next thing is, as I said, since 1965, mostly the whole world has done annual or semi-annual punctual DGA. Over the last 20 years, Also, technology has brought now portable DGA equipment. The advantages of it is mostly you have a much more shorter line of doing the DGA. So you go directly from the transformers, drain valves, you take your sample, and right on the spot, you can mostly do your DGA. So you cut off, mostly you cut off the time of transportation, you cut off the lead time at the where the measurement is going to do. And that has a huge impact, as I said earlier, on the amount of gas you're going to start losing. So again, if you start with 100 ppm, well, in general, if that whole system is under control, you have a good chance, high probability of getting a measurement of around 90 ppm. So the whole system has an accuracy of plus minus 10%, which is pretty good in general. The worst case we've seen is mostly you can get results of 70 ppm. Now, why 70 ppm? Well, because the portable accuracy depends on a couple of factors. The first thing is the detector accuracy. What kind of technology are you using? Each detector has a specific accuracy range. And also, what is the lowest detection limit? Again, every detector, whatever technology you're using to do it, has a different type of LDL. Also, how often the system is calibrated. As I said earlier, every system will start losing accuracy from the moment you buy it. That's the reality of electromechanical system. So if the system, as time goes on, as the system loses its accuracy, if you cannot calibrate it regularly to bring back that accuracy from the same accuracy when the equipment was brand new, well, for sure that will have a big impact on the accuracy of the measurement. Also, what is the extraction and the separation efficiency? There's different way of extracting the gases. Mostly everyone today is using headspace, but there's, depending how the length of the headspace extraction has an effect on how much gas is extracted, especially in the heavy gas. Heavy gas are much more difficult to extract out of the oil than light gas like hydrogen and carbon monoxide. And again, the time to analyze a sample and the container quality. Container quality is very important. Especially if you're using a syringe, there's different type of syringe, how tight they are at the piston, and that's where usually you lose a lot of gas. And also how fast, from the moment you take the oil in the container and you transfer it to your equipment, how fast do you do it? If you do it right on the spot, you have a higher chance of not losing gases and have a higher accuracy of the results, versus if you put it in a syringe and you wait 24 hours or a couple more hours because the operator is very busy and he cannot do it. So during that time, you're going to start losing gas again, especially the light gas. And the next one that has been developed over the last 25 years is online monitors. The online monitors fix a lot of the handling. You have mostly no handling system. It's because mostly those online monitors circulate the oil directly themselves. So there's no chance of losing gases when the oil comes from the transformer directly to the online monitors. There's no chance of losing gases. So if depending on the system accuracy of your online monitors, the best case scenario, if you start with 100, you should end up with the results of around 95, 94, 93%, with an accuracy of around with a system accuracy of around 5 to 6%. In the worst case scenario, you also can end up with a result of 70 ppm. Why? Well, there's different reasons. One, are you circulating the oil? If you don't circulate the oil, the oil, if you're just measuring what's in the drain valve, that oil is stagnant and it does not represent always the right amount of gases that are in that transformer, especially if you have a fault that's evolving, and especially if that fault is a fast evolving. We've done tests years ago where we didn't circulate the oil in the drain valve and measure the gas based from the drain valve versus measuring the gas in another area of the transformer. And what we found out is that in the fault, Sometimes it will take around 18 to 24 hours for the sensors in the drain valve to start measuring the right amount of gas that is dissolved into the main tank. Again, the detector accuracy, the low detection limit has a major impact on your measurement. Mostly if also you cannot regularly calibrate the system. Again, it's an electromechanical system that for sure will lose accuracy over time. So your regular calibration is absolutely critical in those kind of systems if you want to have the best diagnostic. And also what kind of extraction and separation efficiency that you have. You know, each type of extraction system has a different efficiency, and that will have an impact also on how you're measuring it. So now let's look at what are the kind of diagnostic that we're using. The first thing we have is that mostly gas limit. Now there's different type of criteria that have been developed over the years. I'm just showing here 3 of them that mostly are used around the world. You have the Doble criteria as far as what should be the the maximum level of gas that you should find in the transformers on a normal operation. You have the IEEE 57-104 2008, and you have the IEC 60599. Frankly, the majority of around the world are using the IEEE 57-104 2008, as a standard. There's a couple of reasons. One is because often, people are using the first level to set up the alarm limit on their online monitors. So when you're looking at so you have an online monitors doing multigas, when you're trying to set up the warning alarm, often people are using the IEEE numbers on what we call the first level to set up their warning alarm. And potentially you can use the second one, the second level to set up your critical alarm or usually use maybe a lower numbers. Now, each of those, if you're looking at the IEEE, each of those level, are attached to what kind should be the sampling interval and what is the operation procedure. Now, all those 3 standards, the IEEE, the Doble, and the IEC, will not give you a diagnostic. They will just give you tell you that potentially if there is a fault developing and what could be the criticality of that fault and what should be the next step as far as the DGA sampling interval. So if you look at condition 1, if your total dissolved combustible gas is equal or less than 720 and the rate of increase of your TDGC is less than 10, well, you continue your normal operation and you do your DGA. If it's between 10 and 30, you do quarterly, and if it's higher, you do monthly. And as the gas start increasing and you go from condition 1 to 2, well, now your sampling has to increase and your operating procedure has to change. But again, that standard is mostly just like an alarm system. It doesn't tell you if you have PD or if you have arcing. The next one, mostly that has been developed also, is the new IEEE flowchart 57-104 2009, and it's a little bit the same principle, but now this one mostly takes a lot. The 57-104 has been developed on looking at data of over 100,000 transformer and over 1 million DGA over the years, and it's a much more thorough analysis of the data of your transformer, but it needs a lot more data. When you look at it, now you're not just looking at punctual data, but you're going to start looking at the age of your transformer, looking at if it's a seal or a free breeder transformers. And also you need historical DGA data to use some of the table to find what kind of DGA status, if you're status 1 or if you're status 2. So as I said, it's a much more complex, much more thorough analysis that you have versus the previous one, the 57-1 of 2008. The next step you do if you go, let's say, from condition 1 to condition 2, is now you're taking that data, the DGA data, and now you're putting it in diagnostic DGA tools. The one that mostly everyone uses around the world is mostly the Dr. Duval triangle. So you use three gases, your methane, your ethylene, your acetylene, and by looking at the percentages of each of those gases in the overall percentages of those three, it gives you a point in one of the area of the Duval triangle. So on this one here, you see you're on the D2, what we call a dielectric, high energy dielectric. Duval, why Duval is very popular around the world is mostly because Duval not only has developed a mineral oil triangle years ago, but over the years has continuously improved his triangles and developed new ones. So today, when you look at the Duval triangle, you have what we call low temperature fault triangle that can tell you if you have spray gassing, if you have carbonization. You have also triangles for silicone. You have triangles for ester, natural and synthetic, and you have also triangles for OLTC. And on top of it, he has developed a pentagon, who's mostly used if you have not just one specific fault, but if you have a conjunction of fault. And the pentagon, in conjunction with the Duval triangle, allows you to better pinpoint potentially what is the fault and give you much more better diagnostic. The other diagnostic that are being used around the world for years has been the Roger ratio, the Dornenberg ratio, Dornenberg less and less. You have also the IEC 60599 ratio, and you have also the gas ratio. Each of them, again, have been designed mostly for mineral oil. Unfortunately, to my knowledge, none of them has been updated for some of the new oil, especially the ester oil that are being used more and more for the environmental friendly type of oil. But in general, the Roger ratio, Duval triangle, and the IEC 60599 gas ratio, those three diagnostic tools are the most used diagnostic tool around the world. And often what people will do is that they will compare the diagnostic of each of those three. And the past experience from a lot of customers is that if those three tools, Roger ratio, the IEC, and the Duval triangle, arrive to the same diagnostic conclusion, you have a very, very high probability that this is the right diagnostic, that's the right fault being developed in your transformer. Usually it's around 90%, I heard numbers between 90 to 95% if all three tools come to the same diagnostic. So it's a very, very strong diagnostic that can help you to find out what's going on in your transformer, as long as the data is also very accurate. Another one that's being used also, and this is very specific, is what we call the ITRA diagnostic. Now, this tool was developed in Japan, and it's mostly used by Japanese customers and by OEM, and also in Taiwan, because of the OEM in Taiwan have very, very strong historical connection to the OEM in Japan. Again, it's a little bit the same thing that the Roger ratio. You use a different type of gas ratio, and depending where it fits, the results you'll have your diagnostic. It's much more easier to use than the triangle to a certain point, but that diagnostic system has never been really used outside the Japan and the Taiwanese countries. Another one now that's being used, not broadly, but people are starting doing it, is mostly using a diagnostic tool for OLTC. Here's you see an example of the Duval triangle that has been used for specific customers where they are measuring their DGA regularly on their OLTC, and are putting that data into that tool. And here you can see what it tells. Mostly is that you have a normal operation of that OLTC. Now, this is the Duval triangles for OLTCs. There's also other OLTC diagnostic tools that have been designed. You can see two of them. One of the Stennis-Stam ratio, There's also other diagnostic tools that have been used, but they're being used internally. At Doble for the analysis, I heard the same thing for Reinhauser also have their own diagnostic tool for their DGA. Why people are starting, and it's, I think North America is doing it more in general than the rest of the world, but slowly it's getting there. We're starting seeing that with customers in the Asian Pacific area, is mostly because they want to go from time-based maintenance to condition-based maintenance. A lot of customers spend a lot of time every couple of years, stopping their transformer, opening the OLTC, checking out, if there's potentially any problem in it. And often they find there's none. They have to shut it down and put it back, but it costs a lot of money and labors and downtime. So, I know we've worked with some customers in the Americas that were really focusing on getting away from the TBM to a CBM system with some major cost saving. And one way of doing it is naturally doing it like the main tank. You take regular oil sample, you send it to the lab. But also we've seen customers in the Americas and the Asian Pacific also starting installing online monitor system that do exactly what we do for the main tank. They're doing it for the OLTC by measuring continuously the DGA and then using specific diagnostic software to do your diagnostic. So it's a trend that's coming. We think that mostly in the next few years, we're going to see more and more customers starting doing that. Now, how do you read online monitor spec for LDL and accuracy? Because sometimes there's confusion from people when they look at different type of spec sheets. They're not, each of them are not saying the same thing. Normally, when you look at the first thing you have to look is the measuring range. So usually when you look at the measuring range, for a specific gas, like here on the hydrogen, you have what we call the low detection limit, who's mostly the detector sensitivity, and the upper range, which is mostly how high you can measure the gas, either with the detector or by mostly diluting the sample, so that detector can read much more higher, because often detector cannot reach from 2 to 50,000 ppm or 100,000 ppm. So what you have to do in the process is to dilute the sample. That allows now the detector to measure from 2,000 to 50,000. So normally this is the right way to read the measuring range of any equipment, lab, online monitors, or portable. But there's no standard in the industry that oblige manufacturer to write their specification in one way, unfortunately. So often what you will see is this type of spec that says that the measuring range is from 0 to 2000 ppm, plus minus 15%, that's your accuracy, and plus minus 25 ppm. Well, first, there's no detector that reads 0 ppm. It's impossible. Okay, even the best DGA online lab equipment, GC, can measure down to 0.1 ppm. Under that, it's mostly the detector are not sensitive enough. So writing 0 ppm, frankly, is not the right way to do it. And what happened is that people, when you write the spec from tenders, by writing 0 ppm, well, a lot of good supplier will not be able to meet that. The right way of writing it is this way. Specifically on this spec, that equipment cannot read under 25 ppm and up to 2000 ppm with an accuracy of plus minus 15%. And that makes a big difference. So you have to be very careful how you read those specs, especially if you're writing a tender. That you write it correctly so everyone can deliver the right product and meeting the spec what the customer is requesting. The other way, the next one is the accuracy, and that's really very, very important spec in any kind of equipment or any kind of labs. When you look at accuracy, when you look at the lab, when you look at the portable, or you look at an online monitor, you have to look at what we call system accuracy. What does that mean? Well, a system accuracy is made out of the extraction accuracy or efficiency. How good are you extracting all the gas in the time period you're allowing the extraction to happen? How good are you to separate the gas? GC separate the gas very, very well, and that's why GC is the technology that's recommended in the lab, because this technology they're using takes enough time to separate the gas individually, so there's mostly no overlap when the gas arrives to the detection. And then you have the detector or the detection accuracy depending on the technology that's being used, and also how often that detector is being recalibrated. So when you look at it, everyone write their spec differently. Some people will write, what they will do is that they will show the accuracy of the gas extraction in one way, and then the accuracy of the gas measurement. And that's right. It's it's one way of doing it. But when you're looking at that, so if you really want to understand how good their system is, well, you have to add them together. So specifically, when you write a spec like that, what it means is that, let's say for hydrogen, your accuracy now is 18%. And if you're looking at the fall gas, especially the gas that are used in all the different diagnostic tools I showed earlier, the methane, the acetylene, the ethylene, and ethane, well, together, their accuracy of that system, right, brand new equipment starting from at the beginning, has an accuracy right away at 18%. So right at the beginning, you're outside the IEC spec, and it tells you that whatever comes out of that specific equipment, the measurement is not going to be highly accurate. And also you have to do the same thing, sorry, on the LDL. What you see here is that mostly, for the majority of the gas, the LDL is around 9 ppm, and for the hydrogen is 24 ppm. So, again, when you have that kind of spec, that the way it's written, and you're comparing to someone else's spec, you have to add all those accuracy numbers and the LDL number. Another way to do it is that people will specifically just show the detection accuracy. So they will tell you that your accuracy is plus minus 5%, but it's just the detector during calibration. Now, calibration usually happens in the factory. So what it means in general is that my system detector accuracy, when I calibrate it before shipping, is 5%. But it's not my system. My system is higher than 5%. Is it 10%, 15%, 20%? And also, it doesn't tell you what is going to be the long-term accuracy of that system. So it's a little bit misleading, because it gives the false impression that that particular equipment is very, very accurate, when in a way it's not as accurate maybe as some other type of equipment that shows mostly their system accuracy. So here I'm going to finish my presentation. I'm just going to show you a couple of example case study where mostly high equipment, high accuracy has been used by some key customers. Here, this is an Asian transit system installation in Asia on the 75 MVA transformer. What they've done is that they were measuring the multi-gas on the OLTC, and they're measuring dual gas in the main tanks as an alarm system. And what they're doing on a regular basis is that they're taking the data from that OLTC and directly putting it automatically in a diagnostics system using some of the JAL OLTC triangle. It's the same example I showed earlier. So, what you can do with that system is really see if there's any deterioration in that OLTC that will tell you that at that point, the customer has to do some kind of maintenance on that OLTC. Again, the accuracy of that measurement, also on OLTC is not as critical. The response time on the measurement is not as critical as some other faults I will show. But the accuracy of the measurement is absolutely critical, to do the diagnostic using, again, the Duval triangle. Here's another example where mostly the response time and the accuracy is absolutely critical. It happened a couple of years ago in the nuclear Canadian plant after a maintenance, where after the startup, something broke down in their transformer, and you can see in a matter of less than 24 hours, a major catastrophic increase of all the gases, especially the hydrogen, the methane, the ethylene, and the most critical of all, the acetylene, who went up as high as 110 ppm. So again, especially if you have a critical transformer, like in a nuclear plant, the accuracy and the response time of any kind of system you put on those transformers is absolutely important, to be able to make the right decision and doing the right decision in a timely manner. The last one I wanted to show is mostly it's a steel industry in Southeast Asia. It's a very long time customers we've had on a 96 MVA transformer that was a couple of years old. And what this thing shows is that some of the key gas, again, your hydrogen, your acetylene is pretty flat, but your ethane and your methane and ethylene, also all of four gas are increasing over a period of time of a couple of weeks. Again, the accuracy of that measurement is absolutely critical. First, mostly because the system shows you, a change in the behavior of the fault. If you look at it from, the time A to time B, the rate of generation of those gas, was pretty low. But then, in a much more shorter period of time, nearly half the time period versus the A and B time period, the rate of increase of generation of those gas, and mostly all of the gas, has increased by a factor of 4 for the hydrogen, by a factor of 6, mostly for all the other key gas, other fuel gas, methane, ethylene, and ethane. So what this thing tells you right there is that you have a fault. The fault is deteriorating, is getting worse, and the temperature also of that fault is increasing. So again, the accuracy of the measurement is absolutely critical, not just to do the diagnostic, but even to see the behavior over a period of time of those gases in that key transformer. So when you take that data, you enter it in the software, that analyze it using the IEC standard. So we use the IEC 57-104 2008 standard with different level. You can see visually right away which gas has exceeded the condition 1 or condition 2. And then you put it in the different diagnostic tools. So what we've done is we put them in the Duval triangle, the Roger gas ratio, and the IEC 60599 gas ratio. And as I said earlier, when you look at those 3 different diagnostic tools, and mostly all, they are, depending on the measurement time, but mostly all of them come to the same conclusion, that you have some kind of a thermal fault between 300 and 700 degrees. Now, when you put them into the Duval triangle, because the Duval triangle, as I mentioned earlier, has developed more triangle to pinpoint, more specifically the fault. When you use Duval triangle LTF, low temperature fault, number 4 and number 5, it gives you mostly, unfortunately, I apologize, this is very difficult to read. What it tells you is mostly it seems that you have some kind of carbonization happening in that transformer. So you have a low temperature fault, mostly much more closer to 300 degrees C, and you have some kind of an insulation degradation that's happening. So here, that specific customers, what they did, taking that in consideration, they shut down the transformer, took it offline, and open it up. And this is what they found on this specific connection here. You can see mostly where the insulation was mostly completely burned out, and right to the cable. So again, by using the right, very accurate DGA measurement and using very accurate diagnostic tool, they were able to predict that some kind of fault going on in that transformer, and making the right decision to shut it down and do some repair before that fault become even more critical in the operation of their transformers. So as a summary, DGA is a very powerful tool for detecting and measuring, detecting and monitoring development faulted oil field equipment. And the accuracy absolutely influences the conclusion. The first thing, you have to make sure that you take a good oil sample for lab or portable. It's absolutely critical that people follow. There's an IEC spec specifically on how to take a good oil sample in your transformer. If you're going to send it to a lab or if you're going to use a portable DGA, it tells you specifically how to flush. It tells you specifically what kind of container you should use to really minimize the loss of any gases. And also, it's always good to use an accredited laboratory using the ISO 17025. As I mentioned earlier, using gas and oil standard is a great tool to check out the quality of the DGA result that comes out of a lab GC to make sure that they're very accurate over a different range of gas concentration from as low as 10 ppm as high as 1,000. And be careful also when people claim they have accuracy on especially DGA monitors. You said you have to read the small print. I mean, you really have to read and try to normalize the LDL and the accuracy information that are written. Again, as I said, unfortunately, in our industry, there's no specific standard that obliges manufacturer to all write the same way the spec. So everyone will write it one way or another. And to a certain point, it makes it very difficult for our customers to compare apple to oranges. So it's absolutely critical to try to normalize the accuracy numbers so you can make the right decision and when you're choosing your equipment. So thank you very much for attending this presentation. What I'll do now is I'll check out some questions. I don't see any question. Jessica, do you see any question? I don't see them any.
Yes, Serge, we have some questions in the chat box.
The chat box. Okay, where is the chat box?
In the control panel, you should see questions.
Second, just trying to. Okay, do you want? I don't see my chat box. Do you want to tell me what is the question? I'll solve that problem this way.
So we have what is the difference between the photoacoustic method and the IR?
Okay. What's the difference between IR and oh boy, that's a very long one. Photoacoustic to use a combination of infrared, source, and the infrared, goes to a filter that change the light source frequency depending on the gas you're trying to measure. And then when that light source is changed frequency, when it hit in the measuring chamber or the resonance chamber, the specific gas you're trying to measure, let's say methane, that methane absorbs the energy of that beam. Okay, as it absorbs the energy of that beam, the temperature of that molecule increase, and that molecule start to vibrate. And as it vibrates, it creates sound wave. And the photoacoustic has microphone, and it picks up the sound wave. The direct IR goes away with that. What they do is that mostly they will use an infrared beam, a different frequency again for measuring that gas, and you have a sensor that measures the change into the frequency of that specific gas. So they don't go to that secondary step of using the photoacoustic, sound wave. It's a different way of measuring it. Each of them has its own pluses and minuses. So I think it's a different presentation that we can discuss that in a later day versus GC versus photoacoustic versus NDIR. Anything else?
Yes, we have other questions. One is, what is the standard limit for diesel gases?
Sorry, Jessica, I have problem hearing you. There's a lot of background noise. I'm not very close to you. So what's the question?
What is the standard limit for these oil gases?
What is the standard?
The standard limit for these oil gases.
Well, it depend of which one you're using. As you say, if you look at it, let me. There's, let me see if I can. Cannot. My presentation is frozen. Depending if you're using the Doble or as I say, usually people are using the IEEE. That will tell you mostly is this. They don't tell you. Well, usually if your gas and the IEEE, if your gas standard reach the level, the upper level of number condition 3, or if it's in the condition 4, usually that means you have a serious problem. You look at the gas level, especially the acetylene and the ethylene, they're very, very high. Often at that point, the recommendation by the IEEE is that not only you have to significantly increase your DG sampling to see the progression of those gas, see if those gas are steady or if they're going like that, and mostly make a decision often to shut down that transformer. So usually that's when you get to the upper level of condition 3 and condition 4. And again, every customer is different. Some customers are more risk adverse depending on the condition. Sometimes you have no choice. You cannot shut down the transformer for whatever reason. Some other customers are very, very touchy, about the level, especially on the acetylene. So they will make decision to shut down, get the transfer offline, and to go inside and check it out at much more lower level of acetylene. So it's not like there's a specific number and everyone use those numbers. They use that as a reference, and then you look at the different condition and the environment in which you're working. Anything else?
Yes, we have another question from John Tsai. How much ppm acetylene would be required to cause failure of a transformer?
How much ppm of acetylene is?
Would be required to cause failure of a transformer.
Oh boy. Again, it's all depend. Usually people get very worried when they get a level of acetylene over 5 ppm. Okay, you look at some of the standard, that again, the IEC standard, the IEEE standard, the IEC standard. When you get over 5 ppm, people get very, very worried. One of the reasons I think is that from 1 ppm to single digit ppm, usually when you look at the generation rate, it's between 500 and 700 degrees. So usually that's where you get the generation of single digit ppm generated. If you go over 700, that's when your ppm in acetylene increase exponentially. So I think that's why people, when they get into that range, that 500 to 700 based on the level, they get very worried. And that's when they usually, a lot of them will make the decision to shut down their transformers. Again, as I said, it's all depend of the environment, depending on how risk adverse the customer is. It's not. I've seen customers that if they get to 3 ppm, literally they panic and they will shut down their transformer. I've seen some customers still operating transformers with 7, 8, 9 ppm of acetylene. Everyone is a little bit different. Anything else?
And then, Serge, we have another question. Suppose we get high values of DGA. Is it possible in that transformer partial discharge?
If you have high value of DGA, high volume of gases, it's possible to have a discharge? Frankly, I don't understand the question. Hello? Jessica?
Serge?
Yeah.
Would you like Would you like me to repeat the question?
I don't understand the question specifically. If you have high value of gases in DGA, is this possible to discharge in the transformer?
Yes.
An electrical discharge? Yeah, it's always possible. That's what often happens usually when you have a catastrophic failure, is that you have so much gases, especially flammable gases like ethylene and acetylene and high level of hydrogen. If you have a discharge, in that transformer at a very high level of gas, I imagine that's what will create the kind of catastrophic failure you've seen once in a while in some transformers. That's why I said, that's why you look at the standard, the total dissolved gas. The IEEE is using also not just the punctual measurement, but they're using also the total dissolved combustible gas, because that has a big impact. If you have a very high TDGC, and if you have a discharge at that very high level, yeah, potentially you could have a catastrophic failure.
Okay, then we have another question. What is the indicator to replace the oil?
When do you think to replace the oil? When?
What is the indicator to replace the oil?
The indicator?
Yes.
Well, usually it's not the DGA. It's mostly your oil testing. When you do your annual oil testing and you're looking at viscosity, acidity, power factor, all those different oil oil characteristics, especially the power factor, the insulation property of that oil, all those different oil tests you do will tell you, when your oil is starting losing its insulation properties. That's at that point, that's where you're going to have to make a decision. Either reclaim your oil, so usually you bring those used machine that will clean all the impurity of the oil and bring back some of those electrical properties. But at one point, the oil, frankly, has deteriorated to a point that you cannot even reclaim it. That's where, at that point, you will have to change the oil. But not on the DGA. The DGA, is just related to a fault. Okay, so usually, if you're one of the worst thing that can happen, personally, I think, is when you start degassing your oil, when you have a fault and it's creating high level of gases, and you start degassing the oil. This is a band-aid. It doesn't stop the fault, and it gives you a false sense of security that the problem is going away, and the problem doesn't go away, and sometimes the problem get even worse to a certain point. So, I've had many discussions with customers about that some customers will often they do that because they cannot shut down that transformer for whatever reason. It's in the summer and they don't have a backup transformers, and the demand of electricity for air conditioning is up in the roof, so they have no choice. And they have a fault, and a high energy fault. So they will try at least to remove the amount of gases that potentially could create some problem. But that's a very short-term solution. But if the oil is really getting old, it's mostly you have to follow like the IEC spec for each individual test and see how those results are coming. What is the direction over time? And that's why you do it every year. You see slowly the degradation of the oil, because it doesn't happen like that. It happened over a couple of years, where at one point you have to make a decision, as I said, either to try to regenerate your oil or simply change it, and that's usually what happens. Anything else? Because we're running way over time.
Yes, we have a lot of questions in the chat. I would like to leave the audience the time to write all the questions, and then we could answer them by email if you agree.
Yeah, I think that's the best, because I know some people are very late at night, and some of them are very early in the morning. Personally, I'm okay to answer all of them, but yeah, the best thing, send me all the email, all the question. I will answer all of them. I'll send it back to you, Jessica, and we can email it to all the attendees that really appreciate take the time today to participate and to attend my presentation. And again, also you have my email address here on the screen. If you have specific question that you'd like to ask me, I'll be very happy to answer. And also, I have counterpart around the world in South America, Latin America. I have also in Europe, Africa, and the Middle East. That we're all working together, to service the industry. So also, I will make sure that those gentlemen are copied so they can also, you can contact them to any kind of follow-up. So again, I'd like to thank you everyone for taking the time, and have a safe day, and hope to see you again. Thank you very much.